Hello everyone, my name is Tyler Banning. I am a field application engineer for Xsens. I'm here today to discuss handling magnetic distortion in robotic and industrial applications and walk you through some of the things that we like to see when handling magnetic distortion, how they affect the IMUs, and what from an Xsens point of view you can do as a customer to handle these magnetic distortions. I'm going to wait a couple minutes, let everyone keep joining in, and then we'll go ahead and get started. All right, I'm going to go ahead and get started. Quick 30-minute webinar time slot, so get through the magnetic distortion handling and provide some information. And then at the end, we'll have a live Q&A where you can ask your questions and then I'll provide some answers for you. So to start, you can see this is where you can answer your questions. GoToWebinar has a nice little feature where you're able to ask your questions here. And then at the end, when we do a live Q&A, I'll be able to see your questions and provide some answers for you. An overview of the agenda today. First, we're going to start by discussing the effects of magnetic distortions on MEMS-based IMUs, why it's important, why it's necessary to calibrate and understand these magnetic distortions and be able to handle them and provide better output for your different applications. Then we'll discuss a magnetic field map for demonstration. I'll do a quick demonstration of our calibration tool for handling these magnetic distortions. Two different options you have there, as well as additional tools, our representative motion calibration, in-run compass calibration, active heading stabilization, and then we'll wrap it up with our Q&A. So to start, why do we need to calibrate? Well, magnetometers are used by the MTI to determine a reference yaw. This is done by the magnetometers inside the MTI being able to measure the Earth's magnetic field and then provide a yaw heading attitude based on the Earth's magnetic field, and then provide a referenced yaw that is corresponding to true magnetic north. However, if there are magnetic distortions interfering with the MTI's ability to measure the Earth's magnetic field, this will cause different kinds of drift or instability in the yaw output of the MTI because it's measuring, say, a battery, piece of steel, something like that, that is interfering with the MTI's ability to measure the Earth's magnetic field so that you can have a accurate measurement for the referenced yaw. Different types of magnetic calibration will then eliminate these disturbances that are continuously present specifically. With one feature of the MTI and for the Xsens products is that you only have to do this once per installation. So if you have it in your autonomous vehicle, you have to do this calibration once and then you don't have to do it again. It'll be stored in the MTI's internal memory and be repeatedly used over the course of the MTI's life, as long as you don't change the surrounding environment. If you add a battery, add some steel plating near it, then you will need to do a recalibration. Typically, we see two types of magnetic distortions. Distortions that move with the sensor, typically metal structures, batteries, things in the application that are moving with the application. So if you have your MTI in one area next to a battery or a steel plate or something near it that's magnetized, as the ship, plane, UAV, drone, autonomous vehicle moves, then it will stay in the same place relative to the MTI. These types of magnetic distortions are best handled by our MFM, magnetic field mapper calibration, as well as the ICC in-run compass calibration. Additionally, there are distortions that do not move with the sensor. For example, a car that pulls up next to your car and then drives away. That's a spatial or temporal distortion that is not always present, but can affect the magnetic distortion in the environment. Distortions like these are best handled typically with our AHS, active heading stabilization, to best compensate for these kinds of magnetic distortions. The best way to see if a magnetic distortion is affecting your MTI in the application is to refer to the magnetic norm data. That is shown here in the black line. As you can see, it moves quite unstably with the motion of the sensor. That means as the sensor is moving, that it is picking up different magnetic distortions in the area and not creating a stable, clean magnetic environment. However, as you can see after a calibration, this normalizes approximately at 1, and then that indicates you have a clean magnetic environment that the MTI is able to handle, because you might still have these magnetic distortions in the environment, but the sensor is aware of these magnetic distortions, is able to compensate and mitigate them in the output of the magnetic data for the reference heading. Next, I'll do a short demonstration of our magnetic field mapper tool. So first, I'm going to show in our MT manager the magnetic distortions. Magnetic field data. So as you see, I have a MTI 300 mounted to this steel plate. And as you can see, as I move the sensor around, the black line moves pretty crazily with the motion of the sensor. And that is because the steel plate is affecting the magnetometer's ability to measure the magnetic field data for the Earth's magnetic field. Then if I open the magnetic field mapper tool, share that all of you. All right, so now I have magnetic field mapper open. You'll select use motion tracker, then scan. Connected in empty manager still. Scan again, there it is. Then go ahead and start. Now, as I move the sensor around, you can see that it is collecting data. What this data is doing is it is collecting what the magnetic field norm data looks like in the current environment. So as I move it around, you can see this is what the normal magnetic field data looks like. And it's best to get as many rotations, orientations as possible. And ideally what you're looking for is right here, you'll see that it's collecting data samples. Typically, I like to see 15 to 20,000 data samples for a good, strong calibration. And you want to try to get as much of a sphere out of your black data points here as possible. So I move it around. It's important to note to also change the view, because you see it looked like it was filling up, but as you can see, I only had one side. I work towards the other side. Yep. Part can be a little slow, but it is only necessary once. So once you have your solution in your application, it is best to perform this calibration, and then you'll be able to write this to the memory of the device and won't have to do this calibration anymore. Well, this is fairly easy to move around because it's just a steel plate and an MTI. If you have larger vehicles or robots or things like that, there are other options, and we'll discuss that later. But typically, like if you have a small drone or a small ROV underwater vehicle, and you can manually manipulate it and move it around, then that typically works best. Is also, it's a good indicator to also just put the vehicle into its normal operation. So drive your robot around, drive your autonomous vehicle around, things like that. So there's a lot of different solutions for our magnetic calibration. So that looks looking pretty good. We'll go ahead and hit process. And there you go. So you can see here, this red data indicates what the magnetic norm data looked like prior to the magnetic field mapper calibration. Through the magnetic field calibration modules, we can see that now this blue data is what that same magnetic norm data looks like after the calibration. Additionally, there's some advanced results here. You can get a little bit better indications of what your data look like, but typically, just referring to this initial screen is your best bet. Then you're going to go ahead and write to selected devices if you think your calibration looks good. Write to selected device, yes, and it's written to the device. So now this calibration is stored in the internal memory of the MTI. No need to repeat this calibration over and over again, unless of course you change the magnetic environment of the sensor. We'll go ahead and exit here, switch back to MT Manager, where I will show you what the data now looks like. So as you can see, this black line right here, as I move it around, the magnetic norm data is much more stable. Previously, it was following pretty closely to the mag-Y, the green value, but as I move it around, you can see that the data is now much more stable in the magnetic norm data. So that's kind of your key indicator as far as whether there's strong magnetic distortion or things like that affecting your MTI. Moving it around a little bit, straight that, and so that's the general idea of a magnetic field mapper. you use our magnetic field mapper tool, rotate the vehicle or the application around as much as possible, and then it'll write the calibration to your MTI, and you're good to go. And then it's best to check the magnetic norm data again afterwards to ensure that the calibration was successful to your application's needs. Additionally, I'll switch out of this. Yep. Next, I'm going to demonstrate another form of our magnetic calibration. Where the sensor was previously recording data separate, not connected to a PC. So now you can process a log file into a result file. So yesterday, I actually drove around with a MTI 630, our newest product, part of our newest product series, the 600 series. Drove around with it in my car, collected some data, and stored that data as a log file. And then this log file can actually be processed into a calibration result file and be able to demonstrate and convert it into a magnetic field mapper for the MTI 630. So make sure I load the correct file. You see there's MTV files that you can then load into magnetic field mapper and use those to calibrate your sensor. So I have the file loaded, the motion tracker selected, and go ahead and hit start. Do some short processing, and then as it processes, the calibration file will be demonstrated. Interesting to note with this specific calibration is it's an example of a 2D motion calibration. For example, a car isn't going to be flipping over, hopefully. So it really only stays in the same ground plane. So as you can see, the calibration details look very different than the 3D motion calibration I just did with the sensor on the steel plate. And that is perfectly fine. That is an acceptable kind of solution. Obviously, if the car flipped over upside down and created a different orientation that's not in this kind of magnetic calibration, then you may see issues. But since that's not the case for most vehicles, then this kind of application works well. It's common in kind of boats or ground vehicles typically that are typically driving on just the ground plane. So that's just another option as far as how you want to do a magnetic field mapper calibration. And then I could go ahead and hit write file to the select device again, and it would write that file to the MTI, and then I would be good to go. All right, so that was our magnetic field mapper demonstration, both a 3D motion calibration as well as a live 3D motion calibration, as well as a recorded 2D motion calibration from a recorded log file. Those are kind of the two most common ways to do a magnetic field mapper calibration using magnetic field mapper. Like I said, 3D motion, rotating it, getting all sorts of different kind of orientations for your calibration. Additionally, a 2D motion calibration is possible for typically seen in ground vehicles, boats, things like that, that have relatively flat, stay in the relatively flat ground. Next, we have some additional tools when those tools do not work for your specific application. Start with representative motion. Representative motion is very similar to our magnetic field mapper, except it's done all on the sensor itself. So as you can see, the sensor was in a heavily disturbed magnetic field. The black line is moving up and down, is not constant near 1. Then as you enable the representative motion mode, you can see it's collecting data, it's calibrating, doing very similar things as what is done in the magnetic field mapper. Then it stores those parameters in the device, and if it's done well, we'll stabilize the magnetic field. So as you can see, once the ICC parameters were stored, the magnetic field stabilizes along the magnetic norm. Next, we have in-run compass calibration, very similar also to magnetic field mapper and representative motion, except it is being done continuously in the background on the MTI. So it's not quite as powerful or as strong as magnetic field mapper. So typically we recommend doing a magnetic field mapper, but of course, if your solution does not allow you to connect the sensor to a PC where magnetic field mappers run, typically in our MTI-1 series, soldered directly into the internal electronics, then ICC can be very helpful because it's just a quick selection and will run continuously on the MTI. It's doing very similar things. It's measuring the magnetic distortion in the environment and then normalizing those magnetic distortions so that it can recalibrate the magnetometer data and produce a successful, accurate heading. Finally, we have our active heading stabilization. This tool is specifically for sensors not using a referenced heading. So most commonly are VRU systems, very common in indoor applications, indoor logistics robots, things like that, where they are not using the Earth's magnetic field to determine the referenced heading, but rather just using accelerometers and gyroscopes to determine an unreferenced heading. But over time, those gyroscopes and accelerometers can accumulate gyro bias and accelerometer bias. So what the active heading stabilization does is it uses the magnetometers to help stabilize the yaw. The magnetometers can then compensate for the yaw or the gyro drift and stabilize your head. Typically, it's really only used in our VRUs where a reference yaw is not needed. Of course, more details are available on BASE, our support website, where we can dive further into that specific solution. Finally, we have a few more minutes left. If there are any questions, if you want to ask any specific questions, and I'm here to answer your questions. Go ahead and give you a couple minutes to write those in. All right, we have one question demonstrating how to find static distortions. Where I'll just read the question. You have demonstrated how to find static distortions that move with the sensor. However, how do you determine whether there are dynamic distortions, such as distortion from a motor? That's a good question. To start, if you're just trying to find out if there are magnetic distortions, then your best bet is to look at the mag norm data, because that will demonstrate that there is distortion affecting the MTI. And then if you're looking to compensate for those, One option is the active heading stabilization. That's specifically designed for the spatial or temporal distortions that aren't as permanent. However, then you don't have reference yaw. Typically, if you still want to maintain that reference yaw, running a magnetic calibration with that motor running will help, even though those magnetic distortions may not be constant. The magnetic field mapper tool will help in those cases, as well as the MTI's internal algorithms that are able to compensate for kind of short distortions in a magnetic environment based on the sensor fusion algorithms combining magnetometers, gyros, and accelerometers by being able to compare data between those three types of data. Dynamic or temporary distortions are more achievable. We have a question about a team experimenting with a MTI 620, a large mobile robot. They use the sensor to compensate for slip and uneven floors. The heading yaw estimation of the IMU should be rather accurate, less than 1 degree over 10 minutes. Specifically is what they're looking for. That is, and you're asking, so your question is that a realistic expectation for an IMU? So the best bet is to look at the specifications for your the specific sensor you're looking at. So for the 620, off the top of my head, I believe it's 1.5 degrees is the actually the 620, that's a VRU, so not a AHRS. So the 620 actually has unreferenced yaw that doesn't exactly have a ground truth data to compare against. So typically, so we don't provide a specification for that, but typically about 1 degree is possible with a 620. But if you're looking for even higher degrees of accuracy, then our next level up, the MTI 200, would provide even more accurate heading yaw estimation. Any more questions? One question about whether or not the size of the vehicle matters, whether it's a small kind of handheld robot, small miniature size robot versus a larger vehicle or even a larger ship. Typically, it does not matter the size of the vehicle or the application. Really, what the best thing to consider is the amount of magnetic distortion. Of course, the first thing you want to do is try to limit any kind of magnetic distortion near the MTI, but of course that's not always possible in every application. So we look for, so that's why we have magnetic field mapper, ICC, representative motion, tools like that to compensate for those specific distortions. So first, you want to limit the level of magnetic distortion. Next, then use the magnetic calibration tools for any remaining magnetic distortion. I have one last question. It's actually a follow-up to one of the previous questions. The MTI 200 is the higher end version of the MTI 620. It has higher end gyros and accelerometers and magnetometers internally, as well as some improved vibration rejecting tools. So yes, the MTI 200 would be our highest end VRU. Then the medium tier would be then the MTI 620, and then the low end tier would be the MTI 2. So that's the range for our VRUs specifically. And with that, start wrapping it up, unless we get any more questions. All of our documentation is available on our website. Specifically regarding today's topic, the magnetic calibration manual is your best bet for looking at further information about how to run the magnetic calibration, either through magnetic field mapper, ICC, represented motion, all of that information, as well as specific data sheets and user manuals for each of our devices. Additionally, please reach out. We love hearing feedback from our customers, and we look for more feedback as far as what kind of features you're looking for, things like that, as well as if you have ideas for future webinar series topics, things you want to learn a little bit more about from Xsens, please reach out. My email's there, tyler.banning@xsens.com. As well as if you have specific support questions, you can reach out to support@xsens.com. And then if you're interested in purchasing, please reach out to sales@xsens.com. And if you have just general inquiries or general information questions, please reach out to info@xsens.com. And then of course, our base site has all sorts of technical support forum, guides, articles, FAQs, and videos for any kind of future questions or more information that you're looking for. And with that, we are going to wrap up this webinar. Thank you all for attending and look forward to talking to you again.